I am Václav Novotný, and welcome to my tutorial of thermodynamic cycles in energy engineering. In this tutorial, we will have a look at Rankine cycle with regenerative feedwater heating. We will start with a simple process flow diagram of a cycle where is just a single feedwater heater, open feedwater heater, which serves as the aerator. This component has a number 2 on the process flow diagram. The feedwater is heated up to the saturated liquid as it is mixed with the condensing turbine bleed steam. As the steam line is rather long, we will assume a pressure drop in this steam line represented on the process flow diagram by a valve, component number 8. A temperature entropy diagram of this cycle is then shown on the right side of the slide. Now we will have an example calculation of this cycle in Rankine cycle power plant. So, first we need to specify some boundary conditions and assumptions, and the power plant will be coal-fired plant running on coal with a lower heating value of 10 megajoules per kilo. And the boiler will have specified efficiency, specified by single constant value of 0.85. For the cycle itself, we will have specified turbine inlet temperature of 535 degrees C. We will have specified turbine inlet pressure of 9 megapascals. Here. And we will have specified temperature of the cooling water inlet into the condenser, which will be 20 degrees C. Now we will need to specify some temperature differences, which first will be subcooling at the end of condenser, meaning how many degrees below the saturation temperature will the condensate leave the condenser. So delta T sub will be, in our case, 4 kelvins. Then we will have temperature difference of cooling water in the condenser, meaning how much the cooling water will heat up, and it will heat up by 10 kelvins. Now the minimum temperature differences in the heat exchangers. So minimum temperature difference will be specified first for the low pressure part of the cycle, where it will be 3 kelvins, and for the high pressure part of the cycle, where it will be a little bit higher because we want smaller equipment because we need thicker walls, thicker pipes. So at high pressure part of the cycle, the minimum temperature difference will be 5 kelvins. Now we already talked about the pressure drop in the bleed steam pipe. So we will specify the pressure drop in the bleed pipe to be corresponding to 2 degrees at the saturation temperature of the steam. And lastly, we will need to specify some efficiencies of our equipment. So all rotating equipment will have given mechanical efficiency of 0.99. Then turbine will have specified isentropic efficiency of 0.87. Also, pumps will have specified isentropic efficiency, and we will assume 0.85. And lastly, we need to consider some efficiency of the motors or generators. So efficiency or generator or motor will will be in our case 0.97. So by this we have specified our boundary conditions. Now we can move further to make a table of thermodynamic states at different nodes of our cycle. So we will want to calculate pressure with units, we'll use megapascals, then temperature, degree C, enthalpy in kilojoules per kilogram, entropy where necessary, where the units are kilojoules per kilogram and Kelvin, steam quality with unit of 1. We will also need to specify relative mass flow rate, which will be denoted as M. We can put units as kilograms per second. And lastly, we will specify where necessary saturation temperature. Tsat, again in degree C. And we have different states of the cycle, so 1, 2, up to So according to the process flow diagram, we have nodes 1 to 8 and additional nodes for cooling water inlet and cooling water outlet here. In order to make our calculation more convenient, so we will add some auxiliary points, and some points we will also suggest different notation. So as you can see, we have equipment as turbines or pumps with some given real efficiencies. So for more convenient calculation, we will add auxiliary isentropic points for isentropic expansion or compression. So before point number 2, we will put point number 2 isentropic. Similarly, before point number 4 would be for IS, for isentropic, and as you can see, so expansion in turbine at point 6, so we will have 6 IS. Now when you look at the bleed steam, so the steam actually also has to expand to this point. So similarly as with the turbine outlet, we will also need isentropic point for expansion to the point number 7. So we will have 7 IS. And then we have point number 7, the bleed. So just I will add BL to make clear which point it is. And after the pressure drop, the point number 8, in some further more complicated steams, we will call it as point with number 1 lower, but with the notation as FWH as feed water heater. and here we have the cooling water 1 and cooling water 2. Now I will multiply this same table to make obvious where we have which thermodynamic functions and where we have specific given values. So just a little bit rescaling, like this. Okay, this will do. So keep your process flow diagram somewhere handy, and let's fill the values that we know directly. So we know that at point 5 turbine inlet, we know the pressure, which is specified as 9 megapascals. We know the temperature, specified as 535 degrees C. So point 5 is temperature turbine inlet, pressure turbine inlet. Okay, next thing that we have specified is the cooling water inlet temperature. So cooling water, note cooling water 1, which we have here. So we have it here as 20 degrees C. The CV1. Now the cooling water outlet temperature would be the cooling water inlet temperature plus the specified temperature difference on the cooling water, where we have specified that it will heat up by 10 degrees C. So test TCV1 plus delta TCV. Now, since we have the cooling water outlet temperature and we have the minimum temperature differences, so we can actually figure out the condensing temperature. Because if we have a look at the QT diagram of our condenser, so it will look somewhat like this, where the red is steam, the blue is the cooling water. And we can see that the minimum temperature difference will be here on the right side. So the saturated temperature for the state 1 will be outlet temperature of cooling water plus minimum temperature difference for the low pressure part of the cycle. So it actually will, I have to take this away, but saturated temperature for the point 1 will be, let's put it first here, the saturated temperature will be temperature of the cooling water 1, cooling water 2, sorry, TCV2, plus delta T LP. Maybe we can extend our cells a little bit. So here it will be the temperature TCV2 plus delta T at low pressure. So now we move on to the feedwater heater, component number 2 on the process flow diagram. The temperature or saturation temperature at the aerator is usually set as 105 degrees C, so that the pressure is just above atmospheric and the thermodeaeration can take place. So we have temperature here set as 105, and it's basically a boundary conditions. And sorry, it's number 3, as it's pipe number 3, the outlet of the aerator. So the same 105 degrees C will be specified down here. And since I mentioned before that the aerator, the liquid at the aerator is saturated liquid, so that means that the quality is 0. Again, it's basically another boundary condition. So by this we have basically specified all parts of the cycle that we know right away, and we can move into calculations. So the first, the pressure at the condenser outlet will be function of the saturation temperature. So it's function of T sat. So here it will be, as we are using cool prop, so function props SE with outlet will be pressure based on temperature we provide in the saturation temperature, and other will be quality, where we want the temperature at saturation, so the value of quality will be anywhere between 0 and 1. And our fluid is of course water. Now the temperature we have here is in degrees C, so we have to add 273.15 to get to kelvins, and we get result in pascals, so divided by million to get megapascals. Now the temperature at point 1 is saturation temperature minus the subcooling. So here it's the T sat minus delta T subcooling. And from this point at point number 1, we have two thermodynamic parameters, pressure and temperature. The fluid is not at the saturation level, so we can get all the other thermodynamic parameters as function of these two. So enthalpy will be function of pressure and temperature, and similarly it will be with the entropy. So here enthalpy props SE, output is enthalpy with inlet as pressure, pressure in pascals, and temperature in kelvins. And our working fluid is always water. Now again we want kilojoules per kilogram, so divided by 1000. Somewhat similar the function will be for the entropy, just the output will not be H but S. Now the point number 2, it's the pump, so we have the first number 2 isentropic. That means the entropy will remain the same. Entropy at point number 2 is same as entropy at point number 1. And that's all we can specify for now, because we will need to get the pressure. The pressure can be obtained for the point number 3, because we have 2 thermodynamic parameters. So the pressure will be function of temperature and quality. So that's the function that we already had here once before. Just the saturation temperature is the temperature itself, and the quality is specified here. So we can actually see that really it's slightly above the atmospheric pressure, so that the thermoaeration can take place. And just to make our table complete, so the saturation temperature is same as the temperature itself. Now we have to so now this pressure at point 3 will be same in pressure at point 3 is same as pressure in number 2. So like this, and of course also in auxiliary isentropic point. So now for the point number 2, we already have pressure and entropy, so we have 2 thermodynamic parameters. We can calculate the others. Here we will want the enthalpy. So for enthalpy we will want H as enthalpy based on P as pressure, which we have here, and not temperature but entropy, and entropy times 1000 to have joules per kilogram and Kelvin, the basic units. So at number here the enthalpy is function of pressure and entropy. Now, since we have the isentropic enthalpy change, so we know that the real enthalpy change is higher due to the efficiency of the pump. So the enthalpy in the point number 2 is difference of enthalpies H2IS minus H1 divided by pump isentropic efficiency, and this is the enthalpy difference, so we need to add this to the enthalpy at point 1. So it looks like this, and here in numbers it's H2IS minus H1 divided by efficiency of the pump plus enthalpy at 0.1. So similarly as for now for point number 2 we have again two thermodynamic parameters, pressure and enthalpy, and from them we can, if we want, obtain for example the temperature. So I will use let's say I will use this function. But we will want temperature based on pressure, which we have here. And I just want it. So pressure, and no, I want temperature based on pressure and based on enthalpy, like this, and I will get the temperature in degree Kelvin, so minus 273.15, and I get the temperature. So just here to make it complete function of to get the temperature, it's a function of pressure and enthalpy. So now we have the point number 3, where we already know two thermodynamic parameters, temperature, quality. So as we obtained pressure from it, so in basically same sense we can get the enthalpy. Just we want enthalpy as H, and in enthalpy we have units kilojoule per kilogram, so in the end it's divided by 1000. Now the point 3 is before the pump, so we will also need entropy, so basically same function, just we want to get S as entropy, or here to fill this function table, so enthalpy is function of T and X, and same is with the entropy. Now we can move on to the pump. So first we will have the auxiliary isentropic point, isentropic value, so entropy remains the same. The pressure, since we are not now with the pressure we will add one more boundary condition, because typically the boiler has very high pressure loss, so we will add in here, as we had P drop bleed, so we will have P drop boiler, and we will say that in the boiler the pressure drop is 0.3 of absolute pressure at the outlet. Or actually 0.3 absolute pressure at the inlet. So the point at the node number 4 needs to have higher pressure than is at this point number 5. Actually I have it here, just opposite, of course Pressure should be in the pressure column, and temperature in temperature. And point number 3 will be then pressure at number 4 will be pressure at number 4 will be pressure 5 divided 1 minus pressure drop. So here it will be this pressure 5 divided 1 minus and our pressure drop of the boiler. So and the same pressure of course has to be also in the isentropic point number 4. So at the point for isentropic we already have again the thermodynamic properties, pressure and entropy, and same as we used it at the outlet of the pump, of the condensate pump, so we will have the same function for the outlet of the feedwater pump. So the function of isentropic enthalpy is from pressure and entropy. Here enthalpy is function PS, and the enthalpy after the pump, after the real pump, so the function will be again the same as here. So we can almost copy paste it, just we need to log the efficiency of the pump. Yes, and we get the enthalpy. Here it's fairly similar, just we switch the numbers, so it's instead of 2 and 1 it will be 4 and 3. And as you can see, we have pressure, we have enthalpy. Again, same as for the first pump, we can get the temperature. So the temperature is function of pressure and enthalpy. So we moved all the way through the boiler to the point number 5, to the inlet of the turbine. Now, outlet of the turbine, first again the auxiliary isentropic point, so we will need to get both enthalpy and entropy. We have pressure and temperature, the steam is highly superheated, so the function will be for single phase properties from pressure temperature, like this, or we can actually get the same function for enthalpy and entropy as in the point 1. Yes, that is correct, and so is this isentropic point. Again, 0.6 isentropic is entropy same as 0.5. Now the pressure at the outlet of the turbine is the condensing pressure, which we already obtained for the point 1. So the pressure at 6 is same as pressure P1. Now for the isentropic expansion, we can use the same function as for isentropic compression at the pump. and which is here, function pressure and entropy. And for the enthalpy after real expansion, so the expansion decreases our enthalpy drop, so it will be the enthalpy at 0.5 minus now the enthalpy drop, which is H5 minus H6, but multiplied by isentropic efficiency. So the actual enthalpy drop will be lower. So here it's enthalpy at node number 5 minus enthalpy 5 minus 6 isentropic multiplied by isentropic efficiency of the turbine. Of course here is 6 isentropic. Now we have pressure, we have enthalpy, we can get other thermodynamic parameters. So same as here, from pressure enthalpy, or also here, temperature will be function of pressure and enthalpy, and same we will need to get the quality. So let's get the temperature. We can see that the temperature is our condensing temperature, just some rounding, small rounding error in last decimal. And basically same function, just we will a little bit modify it, would be for the quality. So again, function of pressure and enthalpy, but we want Q as quality, and we go on directly the value. And we can see that the real quality at the turbine outlet is 87%. Now we can move to the points of the turbine bleed. So if you look at the diagram, you can see that point number 8 or node number 8 will need to have same pressure as points 2 or 3. So on point number 8, pressure will be same as pressure 2 or pressure 3. So pressure at point 3 is here. Now this pressure corresponds to saturated temperature of this 105 degrees C. So we will also put the saturated temperature same as T3. But be careful, it's only the saturated temperature, as we will see shortly. So temperature 3 saturated is the same. Now the pressure drop across the steam piping was corresponding to 2 degrees on the saturated temperature. So what does it mean? That means that the saturated temperature at point number 7 will be higher by 2 degrees from the saturated temperature at point number 8. So here at point 7, it doesn't matter whether the bleed or isentropic, because it will be the same pressure. So the saturated temperature, let's put it first here, will be temperature 7 WH plus, and we have it as this 2 degrees C pressure drop bleed. So here 105 plus here 2 degrees C. So at the point 7 we already have we know the saturated temperature. From saturated temperature we can get the pressure. So it's the function that we had already here. So we can just copy it. Function is pressure is function of saturated temperature. So here pressure is function of saturated temperature. Yes. So we have one thermodynamic parameter. We have the pressure at the point 7. But we will consider that in the turbine there is constant efficiency across the expansion. So that means that point 7 isentropic will have actually same entropy as point number 5. So 7 isentropic S is the same as 5. Same isentropic expansion. So it was here 7 isentropic, entropy is the same as 5. And now we have pressure and entropy. That means two thermodynamic parameters. We can get from them enthalpy. So basically same as here, very same function. Again, function of PS. So we get the isentropic enthalpy, and same as was the function for the enthalpy after real expansion for the entire turbine. So the same will be the function actually for enthalpy just into partial expansion. So what we had here will be also valid basically here, just H5 minus H5 minus and S7 isentropic times efficiency of the turbine. So here we can log the efficiency of the turbine, and basically use the same function, but of course from the starting point, beginning of the turbine, node number 5. So now we have enthalpy, the pressure remains the same as for the isentropic expansion, of course. So we have enthalpy, we have pressure, we can get other thermodynamic parameters. So for example the temperature, again function of pressure and enthalpy. So it will look like this, or this will go here. And we can actually see that in this case the bleeding steam would be already in two phases. We have temperature same as saturated temperature. So we can have a look what the quality will be. Function remains the same. And we can see that in this case the bleed steam is just slightly wet. But it doesn't need to be the case. The steam can be also superheated in general. So that was the point number 7. Here the point number 8 or 7 going to the feedwater heater. The enthalpy, as this is just a valve, throttling is an isentropic process, so the enthalpy at point 8 will be same as enthalpy at point number 7. So enthalpy, enthalpy at point 8 is same as enthalpy at point number 7. And now we have enthalpy, we have pressure. We can again have a look if we have still saturated, if we have still wet steam, which we do. And we can also get the temperature, which, since we have wet steam, so it needs to be the same as the saturated temperature. So now, after solving the thermodynamic states at all the nodes of the cycle, we will need to figure out the relative mass flow rates. So for the relative mass flow rates, we will write a balance of the component number 2. So in the component number 2 we have mass balance in following form, where M2 plus M8, which is M7 feedwater heater, equals M3. And if we will say that M3 is some fixed value, so we can also write the same equation as M2 is M3 times 1 minus alpha, where alpha will be the relative flow of the steam in the bleed compared to the overall flow to the turbine inlet, plus M7 feedwater heater is M3 times alpha, and this is equal to M3. Which also we can rewrite as we have M3 everywhere, so just get rid of the M3 and we get this. And then we have energy balance, which, now already using the values of alpha, will be 1 minus alpha times enthalpy at the point 2 1 minus alpha times H2 plus alpha times H7 feedwater heater, which is equal to H3. So from this energy balance, we have actually just single unknown, which is the alpha. So we can write that alpha times H7 feedwater heater minus H2 is H3 minus H2. H3 minus H2. The H2 went to the right side. So in the end, alpha is a fraction where we have H3 minus H2 divided by H7 feedwater heater minus H2. So we now implement this in our sheet. So here alpha is at 0.7 or 8, so we will take the 0.8, or first we will actually, for mass flow rate at 3, we can write that it's number 1, and we will have it relative to this value, and at 0.8 it's as we just expressed it. So here enthalpy at 3 minus enthalpy at 2, 3 minus enthalpy at 2 divided by enthalpy at 7 feedwater heater minus H2. So we can actually see that the bleed steam is 12 or almost 13% of the overall mass flow in our cycle. So now when we have these values, so we can actually calculate the parameters as heat input, heat output, and work. Just to put it clearly, so here we have 12 or 13% of steam going through the bleed pipe. So actually at the outlet of the turbine, 0.6 and 0.1 after the condenser, the mass flow rate will be this 1 minus the bleed. So now the turbine is consisting of two parts. So if we want to express the work of the turbine, so it will be first 1, the overall mass flow rate, times difference in enthalpies enthalpy 5 minus enthalpy 7 plus 1 minus alpha, because here in the second part of the turbine there is lower mass flow rate, 1 minus alpha, times H7 minus H6. The heat input to the cycle Q in will be 1 times enthalpy 5 minus enthalpy 4. There is nothing complicated about that, and the heat output of the cycle takes place only in the condenser. So Q out will be 1 minus alpha times H6 minus H1. Similarly, we can also get work of the pump or pumps, where we have two pumps. One pump between nodes 2 and 1, where the mass flow rate is 1 minus alpha. 1 minus alpha times H2 minus H1. And then the second pump, where the mass flow rate is already 1, and difference of enthalpies H4 minus H3. However, this work input of the to pump and output of the turbine, those are thermodynamic works, and we need to then work of the turbine needs to be multiplied by the further efficiencies we have on the way, which are mechanical efficiencies corresponding to losses in bearings and so on. So multiplied by eta m, and then we have electrical generator, which also doesn't have which also isn't ideal and have some efficiencies. So this multiplied by eta generator. In case of pump, the efficiencies will not decrease our power output like is in case of the turbine, but increase our power input. So we have to divide the work by these efficiencies. So now we can implement this into our file. So work of the turbine is H5 minus H7. H5 minus H7 from the point where is the bleed of the turbine, plus 1 minus alpha, which is actually the mass flow rate we already calculated here, times, and now the difference between enthalpies, enthalpy 7 and enthalpy 6. And the overall thermodynamic work needs to be multiplied by mechanical efficiency and by efficiency of the generator. Now for the pump, and here for the pump we need to put all this into the bracket. So we have the mass flow rate of 1 minus alpha, which we already again had here, multiplied by H2 minus H1, difference of enthalpies across the pump, H2 minus H1, plus H4 minus H3, where the mass flow rate is already 1. And this all needs to be divided by efficiency of corresponding to mechanical losses and efficiency of motor, or which is same as efficiency of the generator. So we have 16 kilojoules per kilogram work of the pumps. Now the heat input is straightforward. It's just H5 minus H4, H5 minus H4. And the work output. So in the condenser the mass flow rate is less than the maximum mass flow rate by the bleed of the steam. This is multiplied by difference H6 minus H1, the difference of enthalpies across the condenser. So we get the heat rejected, and now we can calculate the efficiency. So the efficiency of the first efficiency of the cycle, so it will be fraction between net work and heat input, where the net work is just work of the turbine less the work of the pump, and heat input stays. So if we implement this, so the efficiency of the cycle, work of the turbine minus work of the pumps divided by Q in. Now the question is, can I also use the Q in minus Q out over Q in? The answer is that not really, because we have some energy dissipated or rejected on the efficiencies of the generator or motor, or on the mechanical efficiency. So unless we would express that as part of the Q out, so we cannot use this this formulation. So now we'll get to the final efficiency of our plant, of our power plant. So the plant is the efficiency of the cycle multiplied by efficiency of our boiler. So here efficiency of the plant is efficiency of the cycle multiplied by efficiency of the boiler, and we get roughly 31% as the overall plant efficiency. Lastly, we will calculate some overall parameters. So if we would want our power plant to have power output of 60 megawatts, so we will want to get our heat input, amount of the coal that we need to burn every second, mass flow rate of the coal, and mass flow rate of steam going through our system. So if we have this overall power output of our plant, so the Q in plant heat input to our entire power plant is the power output divided by efficiency of our plant. That means for 60 megawatts plant we need to have heat rate of 191 megawatts in the fuel, in the coal. Now mass flow rate of the fuel. We have 191 megawatts of heat rate, and we know the lower heating value of the fuel. So we basically just divide these two with correct units. We have both megawatts. So that means we need to burn about 19 kilograms of coal per second. And lastly, mass flow rate of steam will be, we have somewhere the net power output, unit net power output, or if we don't, we can add it. W net is work of the turbine minus work of the pump in kilojoules per kilogram, and then we have 60 times 1000, so that we have 60 kilowatts divided by kilojoule per kilogram, divided by V net as in kilojoules per kilogram, and from that we get kilograms per second of our steam.